So hi, I'm Rob Clewley. I am an academic by training, and I'm going to be talking to you about some things I've been doing more recently as I've acquired more and more part-time jobs and ad hoc jobs. Now the take-home messages that I want to convey to you in my role as a programmer, but also as a scientist, is how to learn to love constraints that you are dealing with when you're solving problems, and to not give up on, for instance, a high-level language before you've done some analysis about what you might be able to exploit with some problem solving. And the example that I'm going to use is about hash tables, which have been mentioned a couple of times today. And I want to quickly find out who's used hash tables in programming. Okay, good. So I'm not going to have to do too much introduction about those. I'm going to give you an example in the context of one of my latest projects. So this summer, on top of all the other jobs that I already have, I decided to write myself a computer game, like in sense my dream game. Right, so this starts small, you know. So it's going to be a sci-fi survival adventure. It's going to be roguelike, if you know what that is. In the sense it's top-down, two-dimensional, and it can be strategy, puzzles, and some educational components later. Right? So quite a lot of stuff. All right, so I started out with some ideas. A studio name together and a game idea up, and it's taking shape after a few months. I'm not going to really, the concentration here is not so much on the game, but to give you the context for it. So essentially there's a 2D map up here where you're moving around in, and then there's a lot of dense information, which is really part of the aesthetic about the game. But it's a simulation game, and it's meant to be in real time. So here's where it gets interesting. Okay, so I'm trying to solve problems in real time, and in particular, the interesting thing I think about the game is that there's a lot of detailed simulation about the physics and the technology that exists in the game, and that requires a lot of cycles for processing. It's an open world. If I have a chance at the end, or you can ask me later, I have a demo running, I can show you the kinds of things that I mean. But basically, you can walk around and you can mess with the world and change things dynamically in a very flexible way. However, here's the caveat. I'm writing this in pure Python. Okay, so it's like, why would I do that? Why on earth would I do that? Okay, Python is not popularly considered to be a high-performance language. So I'm going to try to challenge that a little bit. But also, I'm good at Python. I've been using it since version 1, which shows my age a little. But I can also quickly build large systems with it. So I thought, you know, this is a good challenge, let's see what happens. And so I'm going to share with you some of the things that I discovered when solving this problem. So how could I achieve some of these real-time features? So let's consider one example on this map that I just showed you. The dynamic updates to visibility when you're moving around. Classic standard problem in computer games. So this is called line of sight and or field of view, two sort of hand-in-glove kind of parts to the same problem. Let's take an example that you saw in that map, where the player is standing there looking east in a small room and then starts to strafe southwards. So here's a snapshot of the game underway. You can see your tiny little player sprite there on the grid, and you're looking eastwards and you have a line of sight problem to solve, right? So you're shadow casting, as it's called. It's a bit like ray tracing, if you've heard of ray tracing in computer imagery, but it's basically the opposite. You cast from the viewer and you figure out where things go. Well, this is extremely simple compared to CGI, but the principles are essentially the same. And you're standing in a cone, which restricts your line of sight around you inherently to a cone based on which direction you're facing. So we're solving multiple problems here. Okay, so what will happen as you strafe southwards, you uncover different areas that become lit and cover up different areas that become invisible, depending on the algorithm. Okay? So you might imagine there's quite a lot of trigonometry and other kinds of computations involving a bunch of math that, and sometimes graph theory as well, that have to happen while you're in the middle of walking around and simulating the rest of the game and doing all the other cool things you want to happen as part of the game. Right? So, but this is a classic problem, and it's been studied to death. Let me tell you though that this algorithm, even a simple one, can grow like n squared with the number of things that you want to detect possible line of sight between, which is kind of obvious it's an area, and we've got two things that scale up in combinations. So this is usually performed in real time by brute force methods every clock tick in the game. And of course that's not a big deal if you're doing this in C++ and GPUs. But you know, as a scientist I often discover that people essentially they throw away CPU time by doing brute force techniques instead of spending a bit of time thinking about smart ways to solve problems. Because you may need those CPU cycles later, and it'll be good to have thought about ways that you could actually find some optimizations if you just look back a little bit. Okay, so obviously I'm doing this in single-threaded pure Python, so let's think about how I would solve that. So first take home then was learn to love the constraints, and there are opportunities for creativity and novelty when you think about these constraints. A great example I like from computer gaming is Silent Hill. I don't know whether you're familiar, but I only learned this recently actually, but the reason that they have this amazing aesthetic is not because someone conceived of this idea as such, it's because the hardware that they were trying to write for at the time was incapable of rendering at a distance that they were trying to get at. And somebody came up with the idea of fogging, and then realized that they could fold that back into the actual game concept, which is just an awesome idea. Right? So let's thinking in that kind of way, what can I do with my design that will exploit what I do have and turn them into features? So I'm trying to maximize the size of my tiles on my grid. I'm only allowing for walls to be on the north, south, east, and west sides of the tiles. So everything's rectangular. I'm only allowing the player to move discretely from tile to tile right now. And I have this cone of forward vision, and there's some sort of maximum range bigger than the size of any room. Okay, so what can that do for me? Well, the restricted FOV creates tension. I think if you play the game, you'll see what I mean. But along with the audio, you're always worried about what's around you, and you have to kind of cope with that. And of course, you get a retro type of feel, which is kind of what I was going for anyway. Okay, so what does this actually let me do in a technical way? It lets me pre-compute the line of sight. Okay, and you're probably thinking, what? Like, what does that mean here? How can you pre-compute something that's dynamically evolving as the player moves around it? All right, well, let me show you. So one of the biggest issues in computer science that you can mess with is the balance between what you do on the CPU and what you do with memory access. Okay. So things that you do every game tick on your CPU, especially if it's floating point operations, that's costly, right? Potentially very, very costly in these tight loops, doing thousands and thousands of times. If you can turn some of that stuff into access to the memory, that is cheap. Plus, memory itself these days is very cheap, right, in terms of money. So there's a lot of opportunities to exploit the fact that memory is so cheap in its use and its cost. Okay. So how do I do that? So I'm going to replace these floating point operations with some kind of hash table lookup. All right, so what does that mean here? It means decomposing, given these constraints that I've set down, it means decomposing all the combinations of player versus wall in a local space, and figuring out how those line of sight combinations could be built up in a modular way, in a way that I can just do a multiple set of lookups at runtime. So let's quickly think about what this means. So I've got 4 view directions, and then here's a little picture of some tiles and all the wall combinations that are possible in that one tile with my types of walls that I have. This includes doors. I'm glossing over doors. It's the same issue. Okay, so we just do some combinatorics. So theoretically, I could take my map and pre-compute all of this given the templates of these pieces, right? Multiply them up. Unfortunately, there's some really big buts to this. Okay. Now, one of the problems is that there are many possible room outlines on the map. Okay, the map can have arbitrary shaped rooms and sized rooms and so forth. Right? And there's many possible player locations. So in other words, even if I have a 50 by 50 tile system for my map, that can easily be up to 10,000 possible player viewpoints within that map. And we haven't even taken into account the fact yet that this is an open world, and I might even be able to change the positions of walls in some sense. Okay? So it's really not a great idea then for me to think about pre-computing this for the map itself, like the actual game map. What I want to do is have a modular way to build up any map on the fly. So this is where I'll just give you a little bit of technical run through. So basically I'm going to build up these dictionaries, and I'll do it graphically for you real quick. So basically what I do is I run some loops offline, and I just place the walls on a grid in different combinations and move them around relative to the player and compute which tiles are going to be invisible, and then append them to a nested set of dictionaries that basically are just loop after loop of these different combinations of positions and directions. So I basically just keep doing that and moving things around and build up this list. And then I can even reuse, I'm not going to go into the details, but I can reuse a lot of these different pieces for the calculations that you do with different wall combinations, because there's a lot of similarities. You pre-compute all of those things, and then you can rotate the east-facing problem that I just solved into a north, south, east, and west set of data with just some rotations. And then you serialize the whole table, which turns out to be somewhere like 26,000 lists of coordinate pairs. And that's not a big deal. That's not even a large amount of data, really, in the grand scheme of things. You serialize that, you reload that at the game start, and then hash tables have order 1 complexity lookup, which means it doesn't matter how big they are. Well, it does ultimately matter how big they are, but we're not getting to that scale that basically you're going to get this extremely fast lookup. So, as quickly to end, let me show you how this will pan out when I use it. I radiate rings of tiles around the player in each tick, and I detect where the walls are. That's one of my lookups that is order 1 fast. Okay, it's much faster than looking at lists. People think to use lists because it's a grid. Okay, so that's a waste. That's a potential waste of an opportunity. The data structure does not have to mimic the structure of the thing that you're representing. Okay, remember, dictionaries are unstructured. They don't have an inherent order, and it doesn't matter for this problem. Okay, so I can find my walls. I look up each wall by figuring out the relative position and then knowing my directions of the wall and my player. That gives me 3 lookups in a dictionary, and I get a bunch of positions out. And then I just make those absolute positions because I've stored them as relative positions. And I do that for each wall, and I build up all the invisible positions on my map. And then I radiate the next level out. This ensures that I get the ordering right very cheaply. I can even pre-compute these rings, so I don't have to do for loops all the time. Okay, so I just layer these up, and there's my southeast wall combo on row 3. Okay, and this is a very, very fast way to have inner loops do this at runtime. So I've got plenty of time in my tick function now to do all the cool simulation stuff that I want to do and keep the retro feel, but also have dynamic lighting and sort of dynamic field of view happening really, really fast. And people said I wasn't going to be able to do it, so I found a way. It's kind of fun. So the take-home message to leave you with is don't underestimate the high-level languages if you think about constraints wisely. And people far, far smarter than I am in Python, like Tim Peters and Raymond Hettinger, have produced these quotes about how code can be basically as fast as C if dictionaries or hash tables, as they're known as dictionaries in Python, if they're appropriate data types for the problem you're trying to solve, it can be every bit as fast as C. In fact, it can be faster than C if you try to do it in a non-smart way in C. Okay? Because you're pushing so much down into the C level by using these data types in a smart way. So I'm going to leave you with that, but if you want to know more about the game or other ways in which I used hash tables in my game, which I have, I've got a laundry list of ways that I've exploited them, then please ask me afterwards. Later on, or check out the website because I'm going to be releasing it in the next few months. Thank you. Question?
Was it a challenge to yourself to do it in pure Python, or did you just not want to use something like PyPy or Python?
It turned into a challenge.
Okay.
Yeah, it just turned into a personal challenge because I thought I teach Python and I want to. I actually have now. I've just embedded a Python interpreter into a virtual console within the game, and my intention is to have the kids. I have kids play games all day, and it's so hard to get them to concentrate, and they're all fascinated by this game right now. And Python's a great learning tool, so I figured I'm just going to try to use Python because then I can have it in the game and I know how to do it already. But yes, it was basically a personal challenge. And at some point I may build some things with Python or other embedded C code if I really need to. But so far I've been surprised at how much I don't have to do that for the type of game that I'm building.
Thank you.
As a scientist, are you taking advantage of any like numerical computing libraries when you're doing
No,
this, or
I'm not.
is there a chance to like take advantage of some of the C compiled like NumPy stuff?
Right, well I haven't, because I'm trying to market this game, so I'm not sure yet whether, I'm not entirely sure the licensing issues with that. So I've actually done all my own, since I'm a numeric analysis to some extent by trade, I've written some of my own in Python and vectorized them, but I'm considering that, so I'm looking at that. Another quick question?
So you can pre-record all the walls and it's just sort of able to insert in the file. So would it be possible to have the game that replaces the shadow style, the shadow table?
Right, so I've been very careful about how I've implemented my interpreter to not allow you to do a hack. There's another layer of API underneath that is faking Python really. So the Python, when you're using Python in the game, you're not literally seeing the bare code. You're seeing an API that pretends to look like code. Yeah, just took me a few weeks. Yeah.
It's been like 10 years, I guess, since I've touched any Python, so I have that somewhat ignorant question. Curious, is the graphics support built into Python now? Or?
Oh, that's a good question. I forgot to mention. So I did say pure Python in the sense that all of the engine that I built is all of my own code, but there is a sort of sprite engine that is inherited from STL, which is called Pygame. And it's old now, but it still works, and it does the basics nicely. So there is a library that I'm importing to do the low-level graphics. Yeah. Well, thanks. Well, I'll be around for a